Hi everyone, today we're going to talk about the accumulation function, which of course has everything to do with integration. This is Dr. Zach and let's get started. For today's lesson preview, you were reminded of the second fundamental theorem of calculus, and g prime of x is 1 over the tangent of x plus 1. Now because your upper limit was x and the derivative of x is 1, you get 1 over tan x plus 1. For question B, you were asked to determine h of x. So perhaps you had to go through your notes and check to see what the derivative of a to the u was, so that you now know that the antiderivative would be a to the u over the natural log of a plus c. Once you do some u substitution, u equals your 2t. du is going to be equal to 2 dt. Substitute, and we will get 1/2 the integral from 8 to 2x, 3u du. Continue with your work, and you'll end up with a 3 to the 2x over 2 natural log 3 minus 3 to the 8th over 2 natural log 3. To determine h of 8, you substituted in the 8 into your equation, so that h of 8 was just a simple substitution problem. And geometrically, what does this answer give you? That would be the area under the curve between 4 and 8. So an accumulation function uses the ideas from your lesson preview, where function g is the net area, or the amount of area over the interval a through x. The net area is positive and negative area combined. If f of t is your positive function, then g of x could be interpreted as the area under the graph from a to x, where x can vary from a to b. G of x is an area, or an accumulation function. Now we must also keep in mind that f of x is a continuous function. I keep pushing that on me. G of x depends only on x, which is the upper limit of your integral. If x is a fixed number, then you have a definite integral, and it has a numerical value. If your x is varying, then you have a function, and x, it can be denoted by g of x. For the next 4 questions, I want you to let g of x equal the integral from a to x. Write an expression for g at 2. So these are substitution problems. I want you to find g prime of x, g prime at 1, and g prime of x squared. Give yourself a few minutes to do this, and then check through your answers. So your first question, as you can see, is substitution. Now, if you know the antiderivative at 2 and the antiderivative at a, you can substitute it in. Your second question, it's your second fundamental theorem of calculus. Again, writing an expression for g prime at 1 is substitution. You're going to get a numerical value. But your fourth question, you should really substitute your x squared back into your original function, so that you remember to find the derivative when using the second fundamental theorem of calculus. So for our first example, we're asked to find 5 different values. The expectation is that you're going to write the integral for each one of these values, and then understand that you have an area that we're trying to search for on our graph. But first, let's write down what we're looking for with each of these values. So g at 2 is going to be the integral from 0 to 2 f of t dt. And the reason this is an accumulation function is because the 0 value does not change as we go along through looking for each of these points. And our last part will be g at 6, which is the integral from 0 to 6 f of t dt. Now let's recognize the different shapes, use our geometric concepts. 0 to 0, of course that answer is 0. When we go to 0 to 1, you see the shape of a triangle, and the area we'll get is 1 for that piece. So there's 0 to 1 is 1. Now we're going from 0 to 2. You should see a rectangle with an area of 2. So our net area from 0 to 2 will be 3. And then we're going to accumulate more. Notice this is a half of a circle. Quarter circle. So we've got 1/4 pi r squared. The radius of the circle is 2. So this area is pi. Now, if we accumulate those, so 3 plus pi as we go from 0 to 4. And 0 to 6, once again, it's a semicircle. It's underneath the axis. So it's going to be 3 plus pi minus pi. So when you integrate from 0 to 6, your area becomes 3. So we need an expression for g prime of x. Be very literal with your problem. So g prime of x is d dx of your integral from 0 to x f of t dt. Use that second fundamental theorem of calculus. You get f of x. For our next question, we want to know where g of x is increasing and decreasing, and we should justify our work. So what do we know? G of x is increasing where g prime of x, which equals f of x, don't forget that, is greater than 0. And this occurs on 0, 4. We know that g of x is decreasing where g prime of x equals f of x is less than 0, which occurs on 4, 6. All right, so now we need to determine any relative extrema. So let's think about this. We want to know where the f of x changes from positive to negative or from negative to positive. So we have a relative, now think about which one. We went from positive to negative. So we have a relative max at x equals 4 because f of x, which equals g prime of x, changes from positive to negative. And that would be your first derivative test. Write an expression for g double prime of x. So g double prime of x is going to be the derivative of f of x, which is f prime of x. Now, if we want to determine where g of x is concave up or concave down, we will know that g of x is concave down when g double prime of x, which equals f prime of x, is less than 0. And this occurs on 2, 4, as well as 4, 6. We also know that g of x is concave up when g double prime of x, which equals f prime of x, is greater than 0, which occurs on 0, 1. So do we have any inflection points? So an inflection point is where concavity switches. Changes. And in this problem, when we look at it, there are no inflection points because it didn't change signs from increasing to decreasing or from decreasing to increasing at any of those values on our interval. So there are no inflection points. So we're asked next to graph a sketch of g of x. So next we want to graph g of x. And if we graph g of x, remember you can plot the points that we found at the beginning of the problem. Think about your concavity, where your function is increasing and decreasing, where you have a relative min or relative max in this problem, and don't forget to put the marks on the problem set to indicate where your points occur. All right, here's a rough sketch of g of x. So we're going to use the fundamental theorem of calculus to determine f of x, but we do know that capital F prime of t is equal to little f of t dt. So if we were to integrate little f of t dt over our interval x naught to x, we know from the fundamental theorem of calculus that that would be the antiderivative, capital F of x, evaluated from x naught to x. And once you substitute, you have capital F of x minus capital F of x naught. Now, specifically, we are interested in solving for capital F of x. Just do a little bit of addition. You will have capital F of x naught, which is your initial value, plus the integral from x naught to x, f of t dt is equal to capital F of x. So our general form of the accumulation function can be written as capital F of x is equal to capital F of x naught, or the initial value, plus the integral from x naught to x of the derivative of capital F of x. And we could also think of it if we're using any value of a, if that is your preference. F of x is equal to capital F of a plus the integral from a to x f of t dt. So we're going to use these ideas in order to solve our next couple of problems. So number 5 is an accumulation problem, and you are given an initial value g of -1 is equal to 3. So you're asked to determine g of 0, g of 2, g of 4, g of 5 using this graph on the right-hand side. For question B, I need the expression for g prime of x and determine whether our function is increasing, decreasing. C looks familiar. There's your second derivative. You're going to talk about concavity. And of course, question D, you're going to make a quick sketch. So take a few minutes, do this problem, stop the video now, and check your answers once you're finished. As you take a look at question number 5, remember to use the correct notation throughout your entire problem set. Figure out your area underneath your curve using a little bit of geometry. You have some triangles. If you want to use trapezoid equations, that's fine as well. Finding the derivative of g prime of x, you notice from the second fundamental theorem of calculus that you get f of x. Make clear statements about g of x, where g of x is increasing, where g of x is decreasing. Explain why, and make certain that you describe why there is a relative max at the value x equals for the value of 5. And also notice that when you're talking about concavity, that you must make very clear statements about g of x versus g double prime of x. An inflection point can only occur when the concavity changes. So make certain that you state that the concavity has changed at x equals 2. So as you can see, question number 6 is a fabulous problem. So make certain that you are using units to help set up your equations. For the first one, how many cubic feet of rainwater, that is what you're looking for. You're also asking whether the water is increasing or decreasing at a certain time. So read carefully, make certain you use the correct notation. And this problem is calculator active. So make certain that you use your calculator to answer the following questions. Stop the video and try this problem. As you complete this problem, make certain that you're using the correct notation and the correct units. So the net rate of change was R of t minus d of t. For question C, you're using your accumulation function. Remember, you're stating that we started at 30. We're going to integrate from 0 to x, R of t minus d of t. Using the second fundamental theorem of calculus, you can figure out that a prime of x is equal to 0 when x equals 3.72. Now you are trying to prove that you have a minimum or a maximum. So we go back to how we worked on those related rates problems. Make a statement as to your answer, and then you're ready to set up question D, but not actually solve it. All right, now I do believe question 7 is a rather fun problem. First, use the second fundamental theorem of calculus to determine f of x. Then, if you actually integrate, you will be able to solve for a and come up with a equals 9. And that's a spiffy little problem. Check your answers with this one, and let's move forward to our next question. Okay, so we've had a little bit more practice with this type of problem. Take a look at where the function is situated and then where we're increasing, decreasing, and concave up, as well as concave down. So your assignment is to complete any lesson practice problems that you didn't have a chance to complete. That's it, and you have a great day.